Thank you very much to the organizers for giving me the chance to speak here this afternoon. So today I'd like to describe how we can use metal absorption lines in the spectra of distant quasars to measure the properties of the circumgalactic medium at the end of the epoch of reionization. Then I will show a bit of how we can use these measurements to gain important insights into things like the emergence of metal-enriched halos, the sources of reionization, and the formation of the first stars in the universe. Now, all of this work is based on data from XQR30, and this is the ultimate X-shooter legacy survey of redshift 6 quasars. Galaxies in our present-day universe are embedded in multi-phase halos of enriched gas that we refer to as the circumgalactic medium. Now, this enriched material wasn't there from the start. It was originally formed in galaxies through stellar nucleosynthesis and supernova explosions, and this material had to be transported from galaxies to halos by means of outflows. Therefore, logically, if we go far enough back in redshift, we should eventually reach a point where the regions around galaxies are no longer enriched. Unfortunately, there are very few observational constraints on when and how rapidly the enrichment of halos actually occurred. Metal absorption lines are really useful for solving this problem because they allow us to measure the properties of interstellar and circumgalactic gas in the early universe. The key here is that the strength of the absorption signature is independent of redshift and only relies on having a bright background continuum source. So in this case, that's a quasar. As photons travel from distant quasars to our telescopes, they pass through any clouds of gas between the quasar and us, and each cloud of gas imprints a series of absorption lines in the spectrum, producing something like what you can see in this plot on the right. So if we're able to obtain high-quality spectra of distant quasars, we can actually measure the evolution in CGM properties over cosmic time and hopefully track the buildup of enriched gas in halos. Now, this is where XQR30 comes in. Over the past decade, our knowledge of high redshift quasars has really exploded. Deep all-sky imaging surveys have revealed hundreds of quasars at redshifts greater than 5.5. However, prior to XQR30, there were only about 10 redshift 6 quasars with spectra of high enough quality that you could actually robustly measure the absorption line properties. The XQR30 survey has quadrupled this number by obtaining high signal-to-noise X-shooter spectra of 30 of the brightest quasars above redshift 5.8. In this beautiful image on the right, you can see about half of the XQR30 spectra. Now, there are a couple of key features here that I'd like to point out. First of all, you can see that these spectra are really beautiful, and there are lots and lots of absorption lines that are detected at high significance. So this is really great news for us. Another important point is that there's virtually no emission detected blue wood of Lyman alpha. Another way to say this is that the Lyman alpha forest is really strongly saturated. And this is because, as Emma mentioned, a non-negligible fraction of the IgM is still neutral at these redshifts. So the blue continuum emission is completely absorbed within a relatively short distance from where it's emitted. Our goal in this project is to use the XQR30 data to measure the typical properties of metal absorbers at redshift 6, and then to quantify how these differ from the typical properties of absorbers at lower redshifts. The first step in this project is to build a catalog of metal absorption lines in the quasar spectra, and I have been leading the effort to produce this catalog. The input dataset consists of the 30 XQR30 spectra, as well as 12 high signal-to-noise archival spectra of quasars at the same redshifts. We developed an automated pipeline to extract a list of candidate absorption systems in these 42 spectra, and then visually filter the candidates to produce the final sample. The plot on the left shows a cutout of a small section of one spectrum where all the identified lines have been colored according to the ion they are associated with. We recover all doublets that we can see by eye, including those that overlap with other systems at different redshifts. On the right, you can see the redshift distribution of the absorbers that we recover. We find approximately 500 absorption systems that span redshifts 2 to 6.5. And this includes a pretty significant number of absorption systems at redshifts greater than 5.5, And these are key if we want to measure the typical properties of absorbers at the highest redshifts. Magnesium-2 is detected relatively uniformly from redshift 2 to about redshift 5.5, but we can only see carbon-4 and silicon-4 above about a redshift 4 and a 4.5 respectively. And again, this is because at lower redshifts, they fall in that region blue wood of the quasar Lyman alpha emission where we don't see any flux and therefore no absorption either. Because our catalog contains absorption systems spanning such a wide range in redshift, it actually enables us to make self-consistent measurements of the typical absorber properties across more than 2 gigayears of cosmic history. This is really important for evolutionary studies because if you have a single sample, it alleviates systematic errors that could be introduced when comparing measurements based on different data sets or analysis methods. Therefore, the XQR30 metal absorber catalog is really a key sample for evolutionary studies of metal absorbers from the end of reionization to the peak epoch of star formation. We will make this catalog publicly available to enable the entire community to make the most of this unique data set. Now, because this is a legacy catalog that will be used for statistical analysis, we have placed a strong emphasis on using reproducible methods that also allow the sample completeness to be robustly characterized. And the completeness statistics will be released along with the catalog to allow users to account for impacts of sample incompleteness on the measured absorber properties. So now that I've described the catalog, I want to highlight some of the exciting science that we plan to do with this data. As I mentioned earlier, one of our main goals is to investigate the buildup of metal-enriched gas in halos over cosmic time. One of the key probes of enriched CGM material is carbon-4 absorption. So by measuring the cosmic mass density of carbon-4 as a function of redshift, we can start to get an initial indication of how the metal content of halos might have evolved over time. Early studies in this redshift range suggest that the cosmic mass density of carbon-4 may drop significantly above redshift of 5.5 or so, as illustrated in this plot. However, there is a lot of scatter in these measurements and the errors are relatively large. This is just because most of the measurements are based on data from just a few quasar sightlines. The statistical power of XQR30 will enable us to make the most robust measurements to date at this high redshift frontier. If the drop in the cosmic mass density of carbon-4 is real, it could potentially indicate that the carbon abundance of the CGM increased steeply in the period leading up to redshift 5.5. Or in other words, this could indicate that redshift 6 may be a key epoch for the buildup of enriched gas in the CGM. However, there are other possibilities for what could cause this signature. The drop could also reflect a change in the ionization state of the CGM. If the UV background is softer at higher redshifts, then a significant fraction of the carbon may be present as carbon-3 rather than carbon-4, and unfortunately, we can't observe carbon-3. So this is really difficult to measure.
2 minutes.
Thank you. Distinguishing between a drop in the carbon abundance and a softening of the UV background is tricky, but we can do it by including other ions in the analysis. For example, the ratio of carbon-4 to silicon-4 is very sensitive to the shape of the UV background because quasars are the dominant source of ionizing photons between the ionization energies of silicon-4 and carbon-4. So by measuring this ratio at redshift 6, we can start to constrain the relative contribution of stars and quasars to the reionization of the universe. Of course, there are many other interesting projects we can do with this unique data set. Absorption line measurements provide important constraints on feedback models because the CGM traces the integrated effect of inflows and outflows over the lifetime of the galaxy. Many different types of feedback models can reproduce the average properties of the galaxy population, but they all give very different predictions for the properties of the CGM. The plot on the right compares the observed carbon-4 column density distribution function to predictions from the EAGLE simulation. The simulation seems to underpredict the abundance of strong carbon-4 absorbers, and this could indicate that the outflows aren't quite efficient enough at high redshift. But again, we face the issue that the measurement errors on these high redshift observations are relatively large. So we hope that with XQR30, we can make improved measurements and investigate which feedback models are able to best reproduce the observed properties of both galaxies and the CGM. And finally, a really exciting project is the search for population 3 stars. So it's not possible to observe these stars directly, but the material released from population 3 supernovae should have a unique abundance pattern that allows us to find regions that were enriched by a single generation of population 3 stars. Given these models, we can use abundance measurements of very metal poor systems to try and isolate these regions. Now, at intermediate redshift, the vast majority of metal poor absorbers show abundance patterns fully consistent with population 2 enrichment, but above some redshift, we must observe a shift in the abundance patterns to reflect the chemical signatures of the first stars in the universe. If we don't see this shift occurring in the most metal poor regions at redshift 6, this places strong limits on the minimum formation redshifts of population 3 stars. And I'm just about done, but right before I finish, I want to mention that there are very few people actively working on these projects, and we are really in need of students to help us out. So if you know any students that would be interested in doing a vacation scholarship or PhD project on this topic, please put them in contact with us. So I'll just leave my summary and take questions. Thank you very much.
Thanks, Rebecca. We have time for one question. So Elaine Sadler asks, can the techniques you describe also be applied to analysis of lines at lower redshifts? Example, redshift less than 2.
Can the techniques also be applied? So in principle, I mean, I'm not really sure what this question means, to be honest. So in principle, you can.
Let me jump in. If I had X-shoot a spectra of of lines at redshift lower than 2, could I still do the same sort of analysis that you've done? I just wondered what the reason for stopping at redshift 2 was in your study.
Oh, okay. So basically, we just can't detect any lines at redshift less than 2 because of the Lyman alpha forest. So with the lines that we have, so we got to magnesium. Magnesium 2 is the longest wavelength line that we have. And so given that the quasars are at redshift 6, the Lyman alpha emission is at about 850 nanometers. So the lowest redshift we can detect magnesium 2 absorption is about redshift 2. But that's the only reason why we stopped there.
Okay, thanks.